This is Jennifer Martinez, here to talk about one-sided limits. I'm going to start with an example. What is a one-sided limit? Well, it's when you have a little minus or a plus in the exponent. The first one is called a left-hand limit. And when there's a plus here, it's called a right-hand limit. And you can see from this example, as x approaches 2, what this is going to mean is as x approaches 2 from the left side, it's getting close to L1. You can also think of it as values a little bit less than 2, smaller than 2. As x is approaching 2 from the right, the y value, the f value, is getting closer to L2. So that's why the right-hand limit is L2 as x approaches 2. Let's read what the book has to say about this. This is from our textbook. When we write the limit as x goes to 2 of f of x, what does that mean? That means as x approaches 2, what is the value of f of x from both sides? It says here that we mean the number that f of x approaches as x approaches 2 from both sides. There it is right there. We examine values of f of x as x approaches 2 through values greater than 2, 2.1, 2.01, and so forth. That's coming from the right-hand limit, and values less than 2, 1.9, 1.99. Correct. So that is the left-hand limit. If we wanted x to approach 2 only through values greater than 2, that's when we write this. So we know that this one we saw was, in this case, was L2. For the number that f of x approaches, assuming such a limit exists, and similarly, this one is going to be the right-hand limit, and it denotes the is obtained as x approaches 2 through values less than 2. So we know this one from our example was L1. By the way, this one does not exist. Sometimes we write DNE for does not exist. And why does it not exist? Because the left-hand limit, it approaches 2 different values not from both sides. On the left side, it's approaching L1, and the right side, it's approaching L2. So for this limit to exist, we need that the left better equal the right. In general, the limit as x goes to c of any f of x exists if and only if the right-hand limit equals the left-hand limit. And when it does exist, obviously, that would be the answer of our limit. So let's look at the following example. We'll leave that up there. Okay, so what is the limit as x goes to 1? And that means, again, left-hand limit from the left. So x is going to 1 from the left. The y value looks like it's 1. What about from the right? It's kind of hard to say there, but this is going on to infinity. So I'm going to assume this is a negative infinity. I do not write does not exist for negative when it's either for left-hand limits or right-hand limits, because it either usually goes to positive infinity or negative infinity. Technically it does not exist, but it's going to a very large negative number. So we like to indicate that by putting negative infinity there. So obviously this one does not exist. The left is not equal to the right. Whereas part D, as x goes to 2 from the left, it looks like 1. As x goes to 2 from the right, it looks like 1. So the limit does exist here, even though there's a hole. Limit just exists because it's going towards 1 from the left and the right. If I said what is f of 2, just to give another example there, this would be undefined. If it had a dot there, it would be 1. For instance, like f of 1. F of 1 is equal to 1 because there was a dot there, even though the limit did not exist. So you have to be careful with that. Okay, let's just look at a couple simple examples. So here is a table of values near x squared. So it starts with 1.9, 1.99, 1.999, and then it does 2.001, 2.01, and 2.1. So if you take your calculator and put 1.9 in for x squared, you should be able to get these values. So from the left, we're going to be looking at these values. These are the values from the left. Left of 2. Left of 2, 1.9, 1.99, 1.999, it looks like it's going to 4. On the right would be these values. Right of 2. And as I get closer and closer to 2, if I start with 2.1, then go to 2.01, 2.001, it does get closer and closer to 4. So approximately 4. So therefore, the limit is 4. What about this one? You can do this two different ways. You could look at a graph or you could look at a table. If you looked at a graph, you could graph this on your calculator. It looks something like this, where this is x here. So as x is going towards 0 from the left, we don't say it does not exist because it's going to negative infinity. From the right, the y value of 1 over x is going to positive infinity. So here, we can't say positive or negative infinity because they're different. So this one we would write does not exist. All three does not exist, I get it. But we specify that to let us know how is it going to a large number, is it going to a negative number, or is it going to no number at all? We could have also made a table as x, so for part A, we're looking at it as x approaches 0 from the left, so numbers that are a little smaller than 0, like negative 0.1, negative 0.01, and negative 0.001. If you plug these in here on your calculator or make a table, you would see that they're getting larger and larger negative numbers. Versus if I plug in just 0.1, 0.01 on the positive side, they would be 10, right? 1 over 0.01, 1 over 100 is 100, 1,000. You can see that it would be positive. So you could either make a table or you can graph if you're not sure the answer. How would it change if I made this 1 over x squared? Well, I'll do this one by a graph. If you graph this on your calculator, you'll notice you'll get something like that. Make that a little neater. So here, the first one's obviously different because now when x goes to 0 from the left, even if you plugged it in, you're going to square it. And so you're going to get a positive infinity, which you can see here from the graph. As x goes from 0 on the left, it'll be a positive. The right, obviously, is positive infinity. So we do not write does not exist for this one. Even though it does not exist, we write positive infinity. It lets us know that no matter which way you go, you're going to positive infinity. Okay, let's look at example 1 from the book. You could make a table or use your calculator. I'm going to just go ahead and use my calculator. I'm going to type in y equals. I'm going to go to absolute value. Absolute value is in the math, right below the alpha. Once you're in math, you're going to go to the right, hit the right arrow for this number here. So you can see num is highlighted there. And number 1 is absolute value. Oh, that's nice. So then I'm going to type in my x minus 2 using the xt theta comma n that's right next on the right of the alpha. And then I'm going to hit the right arrow a couple of times to get out of there. Hit the divide for dividing, and I'm going to go ahead and put that in parentheses, the denominator in parentheses. And if you graph that, oh, that's what it looks like. Now let's zoom in. Zoom number 2 is zooming in. Press enter after you zoom in. You could also just change your window. So it looks something like that. So let's go ahead and graph that. If I wanted to regraph that, that would be 1, 2, it looks like. And it looks like it's 1 this way and 1 that way. Right, that's the x-axis. This is going to be -1, and this is going to be 1, it looks like. Since I just used the standard window, and so each scale, each label here is just 1. Okay. By the way, there is a hole at 2. I'm going to add that hole at 2. There's no value at 2 because f of 2 is actually undefined. F of 2 is undefined because you would put a 0 in the denominator there and that wouldn't make sense. So I'm going to put a hole there. So part A, what is the limit as x goes to 2? See, the right and the left go to 2 different values, so that one does not exist. But part B, we could talk about the limit as x goes to the right. That would be a little bit larger than 2, the right side of 2, and that looks like it's 1. Now let's look at part C. As x goes to 2 from the left, a little smaller than 2, the y value is -1. So it makes sense that the limit as x goes to 2 does not exist here. Hope that helps.